So 1 minute to go, or should we start now? So we are on time? Yes, let's go then. Um, Welcome to the ICCRG meeting, last meeting of the day. So hang on there. Um, a bit of, so maybe some of you never saw me on site here. I'm one of the co-chairs, Simone. I'm representing Reese and Vidi here today. So we are going through the Note 12 slides. Hi, Reese. It's early for you now. Yeah. So a bit about the fact that the meeting is being recorded, and some of you may have indicated through the color of your linear if you want to be recorded or not. But here are the rules. Um, Also the rules to use the chat and also to use the mic. Intellectual property is probably known to many of you, but nevertheless stated here again. RFC 43, 43788 for reference, if anybody wants to clarify anything. Audio and video recordings. Here is actually the information for whoever indicated that photos or image should not be taken. If you come to the mic, if you turn on your camera, so you are consenting that your image is being available in the recording. Privacy and code of conduct. We have now an RFC 7154 for the code of conduct for the IRTF. Please have a look there. Yeah, the other information is pretty standard. So this is research group, so as such we are not doing standards development, but we have nevertheless the chance to publish documents in the RFC series as experimental informational documents. This is also just for info. We are still having people entering the room. The agenda, a bit shorter. We have one talk in the last minute canceled, but somebody asked for a few extra minutes, so go and grab 5 minutes. So it looks like the first presentation is with Jason. Then we have an update on the pacing protocol, the pacing draft from Michael, and Zili also presenting research. And at the end, we are going to have a tutorial panel. I hope discussion is lively in this panel, and I hope we addressed well some of the comments that received in the mailing list. So we hackathon update. Oh, that was new. Thanks, Reese. Do you want to take that? Do you want to say something here?
Yeah, I didn't want to say too much about this because we just had a presentation in CCWG. Mohit presented a couple of slides. Mohit, if you can just wave so people can find you after the session if they want to know more about the congestion control testing efforts that went on this past weekend. And thank you ever so much for your work and for everybody else's work who was involved in the table.
All right, then I think we are on time. Last slide. If there is no other questions, we can go on with Jason. Reese, you're.
All right. Thanks, everybody. Boy, it's cold in here. My God. Um, all right. So I think this is, congestion control related. So for those that haven't been in TSV working group for a little bit, uh, we at Comcast have deployed dual queue low latency, so L4S and NQB. And we noticed some really interesting things as we deployed, as part of that effort, new active queue management algorithm in our access network, and sort of this interplay between speed tests, bandwidth tests, and the introduction of AQM and new congestion control algorithms. So what we did, just as background, starting in I think like January or so, we started deploying in the production network. Right now we're at a little bit around 7.5 million, probably 7.75. So roughly speaking, about 270 million end user devices connected. And what we've deployed as part of this are sort of two things. One, in the CPE that's in the home router, and in the CMTS, which was the next hop up into the access network, we have done first active queue management, which is DOCSIS Pi, and that is for the classic queue, so for all existing sort of application traffic. And then in addition, we've created a second queue. This is for L4S and NQB, and you can look up some of those RFCs or internet drafts if you want more information there. So that was sort of what we were doing. We've been working on that and deploying for months. But what was really interesting as we began this at some level of scale is this sort of tension between that change, really fundamental changes in the active queue management, downstream and upstream, changing congestion control algorithms, and then these bandwidth tests. And they're really used for a few reasons. Number one, for service assurance. So we run 700 to 800,000 of those tests automatically every day, sort of randomized geographically across time, et cetera, to just sort of make sure that the end users are seeing the sort of capacity that they'd expect. And then, of course, for troubleshooting. So anytime customers like opening a ticket and saying, we're going through a process on their app saying, like, my speeds aren't correct, or I'm having trouble with my service, it'll run that test in the background just to see what's happening. And then, of course, from a compliance standpoint, for the regulators, we have to provide a broadband label that shows at peak hour and off-peak hour what bandwidth is achieved compared to what is advertised. So the interesting things that we started seeing is, and by the way, sorry, let me go back and talk about our existing capacity test. So first off, it's embedded into our home gateways. So I mentioned that we run 700 to 800,000 of those tests per day. So think of the CPE, the home router, running embedded Linux essentially, and software called RDKB. That has in it, an iPerf test that'll run, capacity tests, and runs using TCP. And a whole bunch of other stuff happens in the background that's baked into operations in a lot of fundamental ways. The key parameters of those tests, and I'm sure this is familiar to many of you that have done TCP-based speed testing. It's of course using TCP as the protocol, although with iPerf and other tests you can use UDP if you want, and of course QUIC, I suppose. You can configure the number of parallel connections, the omit time, and the duration. And I'll show you what that means here. So the omit time is really the ramp up time, and the steady state is the duration. So essentially what you have to do with these speed tests is throw out the time that it's trying to ramp up, doing TCP ramp up. And what we found with some of the newer AQMs is that ramp up time takes a little bit longer. It's a little bit smoother. And as a side effect of that, it's less disruptive to other flows. So it's sort of expected as part of the design. And then the steady state duration, that tends to be longer and longer the higher capacity of the connection. So if we look at that duration on a 100 meg downstream connection or a 1 gig downstream connection, typically that duration is going to run a little bit longer when you have higher bandwidth. Obviously, in terms of connection, these are just some screenshots from research that folks have posted previously about number of connections in these TCP tests. And obviously, we're using multiple connections. That is also similar to the types of things that people do in browsers, et cetera. They're not just opening one connection, they're opening lots of connections. So multiple connections in parallel in a speed test are more applicable. So as we started deploying, this is a picture from one of our vCMTSs, which is a virtual CMTS. As you see, all the way over on the right, with this blue line, which is retransmits, suddenly went to almost zero. And the green line is sort of there, which is our POA, which is percent of advertised. And so that's sort of saying, are we achieving what we're provisioning? And unbeknownst to us, we're doing this deployment, and then someone from the operations team says, hey, we've got some weird things happening with our measurements. First and foremost, we don't see any retransmits. What's going on? I'm like, wait a second, that's a great scenario. We're glad that we don't have retransmits, especially for real-time traffic. And then they also noticed this sudden oscillation of the bandwidth measurement. And so as we dug in, we realized that, what was happening was we were having this very interesting, sort of interplay of, we've got this new active queue manager, but the number of connections, the omit time and the duration time probably need to be adjusted. And so we paused for a little bit as we assessed this to make sure that we understood all of the data, because really fundamentally, if these sorts of measurements go out of range, if you will, it triggers a whole bunch of other operational alarms and people looking at what's changed and why, et cetera. And so it's important for us and for any network operator to do that. So we started playing with all of those parameters. What are all the new knobs that we can tune? And LLD, by the way, is just low latency DOCSIS. So one of our internal acronyms, if you will. So, we started, tweaking everything from, number of parallel streams to the seconds of omit to the seconds of duration, just to see how those things change. And the important thing that we had to sort of explain to some of the operational folks internally was, what we've really fundamentally changed is we've introduced this new active queue management, CCA, and the side effects on the actual real world user behavior, if you think about real-time communications and so on, are very, very positive. The working latencies went down by half, really dramatic improvements as a result of that AQM. But you have here the synthetic test, which is really not a great simulation of end user behavior, even though everybody uses web-based speed tests or TCP-based speed tests. And so we had to first say, let's make sure everybody understands this test is a very artificial test, and we're not going to sort of tune the way that the congestion control algorithms work in order to score a better grade on the test. What we should be doing is tweaking the parameters of the test itself to reflect what's really happening from a bandwidth standpoint, because the bandwidth did not get reduced, for example, by introducing a new congestion control algorithm or by introducing a second queue. And so we did some of those adjustments, and this is a corresponding latency test. So this is what we went back to in terms of the user experience about why did we introduce that new active queue management algorithm? Why did we do dual queue, for example? And it's all about, not bandwidth, but really latency and working latency or network responsiveness. And so, when we started turning on AQM, downstream AQM in this example, we immediately saw these drops, and that corresponds beautifully to a much improved user experience. So again, it was this sort of internal discussion of, we have an AQM that results in really positive working latency improvements, which was the goal of the AQM and the goal of dual queue as well. But it doesn't necessarily correspond to this artificial speed test. So how do we do things? So, the end result was that we made a bunch of changes to all of those parameters, the duration, the omit time, and the number of parallel streams. And we made those changes in the field, and we saw all of that sort of oscillation, revert back to the normal types of things. And again, it just sort of reinforced, especially for some of the operations teams that are not very well acquainted with all the things that we talk about here at the ITF and IRETF and elsewhere, that, hey, this is not really representative of necessarily user experience, because that's more some of the things that we saw before around latency. This again is the result of this synthetic test tweaking. But again, it got us back into range so that we can better understand and accurately measure the real capacity that we're providing. And so this was sort of a positive result as we finish that. So I think as a quick wrap up, and then I'm happy to take any questions, I think we've really had a lot of, over the years, fundamental ways that these TCP-based bandwidth tests have been used. And there's all sorts of processes behind the scenes from a service assurance standpoint that depend on those things that are running on our user gateways. And making any changes to those parameters, or when those parameters change as a result of something pretty big like a new AQM in the access network, causes a lot of secondary sort of knock-on effects. And it's important to open up those discussions with operations teams that depend on those things and see a sudden change, and explain exactly why that changed and what was it in the congestion control algorithms that changed. And in many cases, you have to describe first and foremost what is a congestion control algorithm. But those are important things to keep in mind, and it's a very fundamental thing, and I'm sure every network operator has tests like that embedded. The other is obviously what I said before, which is CPE or access network, things like new AQMs, in our case DOCSIS PI, L4S, and QB. Anytime those are introduced, these things fundamentally change, and you're going to have to take a look at how some of those test parameters are configured, and making sure that the devs are aware of that. And then the fundamental sort of challenges or questions that we face in the long term are things like, are there other methods of measuring or assuring that we're providing bandwidth to end users that are somewhat less influenced by congestion control algorithms, particularly AQMs like Pi and CODL and so on. And then, is it time, and this is a longer term question, we've been talking about this for a while, to sort of de-emphasize bandwidth tests. And I'll say this, at a high level, as we've moved to 1 gig, 2 gig plus symmetric speeds, the only application that uses that amount of bandwidth is a speed test. There's no user application that uses any of that. And so it creates this question of like, why are we still doing those tests? Why are users being presented with like, oh, go run a 1 gig symmetric speed test that is completely unrepresentative of what you're doing with, WebEx and, using Zoom and FaceTime and Netflix and YouTube, et cetera. So, I certainly, as I note, easier said than done, because there's so much momentum around this. And of course, introducing new latency-focused measures, such as responsiveness under working conditions that came up in the prior session, and other kind of working latency tests as an alternative, because those are much more correlated to end user quality of experience than bandwidth tests are these days, or at least in those market areas that have multi-hundred meg or higher speeds. So that's the end of the slides. I'm happy to take any questions.
Mo, did you roll this out in one shot, or was it phased where you first did the downstream AQM by itself, Universal Pi, and then later did dual Q? I'm wondering what sort of relative differences did you see to the latencies just by a Universal AQM and then versus the dual Q added later?
Yeah, so we definitely sort of did it in a phased manner. As anybody would operationally, we deploy a few and soak it, and then do a phased deployment. We actually turned on downstream AQM first, because that was a sort of core VCMTS feature, And for that, we saw the working latencies basically drop by half. So huge improvement. We were like, wow, we could just do that and call it a day. Like that was a huge win, right? Doing dual queue on top of that was sort of half again, and really for those, and this came up in Stuart Cheshire's presentation in a prior session, we got pretty close to idle latency there, which was great. And that, from his standpoint, he said that, achieved his design goal or what he had envisioned for things like L4S. And so we were really delighted to see the same thing. We've seen that with some of our, in particular, cloud gaming partners, where it was really close to idle latency. So we felt that that was a huge win and worth it to add the second queue as well.
So you saw roughly the same order of benefits in each phase.
Yeah. So
Great.
again, just top line, working latency with downstream AQM as a feature, talking about half, 50% reduction in working latency, and then doing dual queue and seeing applications using dual queue, you get pretty close to idle latency under working conditions.
Great info, thanks.
Yep.
Alessandro
Sorry.
Ghettini. Sorry, go ahead.
Sorry, I don't want to interrupt, but anybody that comes to the mic, please say your full name.
Alessandro Ghettini, Cloudflare. I might have missed a bit from the chart. It was a bit hard to read. So one of the lines was the retransmits. What was the other line?
The other line was the bandwidth, megabits per second.
Oh,
if
I
you
see.
will.
Okay.
Yeah.
So the experiment basically was you run hyperf or whatever for a set amount of time, and then you measure the bandwidth across the whole experiment.
Right. Yeah. And so if I go back to it, since oops, there it was. This one, I think.
Right.
Yeah.
Yeah.
Yeah. So when you see this here, this timing,
Yeah.
that's when the downstream AQM was introduced.
Yeah.
And so you suddenly saw this oscillation of, a lot of variation in terms of the bandwidth, because I think really what's happening is those connections are sort of constantly seeking,
Right.
capacity, but there are very few of the connections, beforehand. But then retransmits went down. And, so the green line, which is the downstream advertised rate, megabits per second, excuse me, as you added more connections and as you, extended sort of that omit time and extended the duration, allowed that to smooth out a little bit. And the retransmits was just funny, just as an aside. And we were trying to explain, like, hey, if we're in a video conference right now, like, you don't really care what happened 2 seconds ago as a retransmitted packet. You want to see what's happening now.
So, I'm not like super up to date with the whole queue management improvements, but I would have expected that like hyperf traffic would go on the maybe like classical queue or like not the not low latency queue.
Yeah, for sure. And this is only the classic queue. So this is
Right.
not the
So
low latency queue.
So do you think that the sort of variation is due to maybe having less capacity because some of it is dedicated to other traffic?
No, because the capacity is unchanged at this point. There's not even a second queue in this example. It's just introducing a new form of active queue management. And I think it's really whether you go to, and I see, Frank's next to you, so he can probably speak more to this as well. But, when you talk about some of these new active queue management algorithms, you're really fundamentally, I think, in my sort of limited understanding, changing the sort of the priorities of the types of traffic handling. So, for example, a real-time flow before this was going to be losing out if you're overwhelming it with lots of queue building traffic. And so you're in the scenario where it's way better for real-time interactive traffic. And as a result of it, to sort of have the more accurate representation with this type of test, synthetic test, you had to add more connections, so on.
And last question, were you testing with any specific congestion control algorithm, or was this like default on
yeah, so in the DOCSIS network implementation, it's called DOCSIS Pi. And it's basically an implementation of the Pi AQM just for DOCSIS, so you can read up on that. But a lot of those are very similar, whether it's FQCODL, pie,
So,
cake, etc.
I'm asking from the the endpoint sender perspective rather than the queue
So
management.
endpoint being the CPE or the user endpoint, like a user.
The one
computer.
that is generated the traffic, right?
Okay, so the one generating the traffic is in the router, the home router, if you will, the home gateway, and that's also running a DOCSIS Pi
But it's,
algorithm upstream.
is it like cubic or whatever, like BBR?
No, it's a Pi based congestion
I see.
control.
Okay. Yeah.
Yeah.
Okay. Thank you.
I think we don't have more questions in the chat. We are good.
Is there one more?
One more? Yeah, go.
Yeah, Mohit from NITK. Thanks, Jason. I wanted to ask a question. Yeah, one of the slides, the slide number 4 and slide number 8. Yeah,
That one? Which one?
4, one more back, one more. Yeah. Yeah, sorry. So can you just tell what is the difference between the lines that we see ramping up on the left side of the aggregated measurements, and which one is representing what?
Yeah, so these are some, upstream and downstream bandwidth levels, and the dashed line is sort of the goal of where the tests we're trying to get to. Essentially, just sort of showing that, in this case, put aside necessarily what the numbers actually mean. It's just you've got TCP ramp up time, and you want to exclude the ramp up time from the speed test measurement itself.
Okay.
And the concept here being, because with the newer forms of active queue management, that ramp up is a little softer, if you will. You're extending that initial ramp up time, so you're omitting a little bit more and moving the measurement box, shifting it over to the right, if you will.
Okay. On slide number 8, yeah, that one.
Yeah.
So what's the difference between the plot on the left and on the right? So we see the
these are two different modems. Sorry. So when we deployed on gateways that we call XB6, 7, and 8, and each one of those XB6, XB7, XB8 have multiple different hardware, chipset providers.
So these are from two different chips.
Yeah. So we try to make sure that they're all looking the same, and that there's not some performance issue related to some of the chipsets.
Okay. Last question is, do we have any technical report available to refer this test that you've done?
No, but contact me offline. Happy
All
to
right.
tell you more.
Thank you.
Thanks.
So next, Neil.
Neil Cardwell, Google. I had sort of two questions. One was, what was the number of connections that you ended up with? The number of parallel connections?
Right. So let's see. I think I have it somewhere in here. Oops. Yeah. So I think we ended up with 4 in the end, but I think it's still a little bit of an active, tweaking that's going on. So it might be slightly different at this point.
I see. I guess it seems there's a potential concern that changing the number of speed test connections means that the speed test may or may not represent real actual client workloads. Like, I guess there's a concern that it might be a little bit of sort of just changing the benchmark to make the numbers look good, even though it may not match real workloads. And it might be sort of papering over, say, for example, bugs or flaws in the end host congestion control algorithms. Any thoughts?
Sure, great question. When we compared this to the Cloudflare speed test, the Ookla speed test, and like 5 or 6 other speed tests, those tests did not show any difference before and after the downstream AQM algorithm. So we felt pretty strongly that it was an artifact of just our test. That has spurred a lot of other conversations about our test as well, given that all of the other external tests didn't really show any degradation or change.
That's interesting. I guess they may have already been using lots of connections or something. Is that the theory?
Yeah.
Okay. And then my second question was, it seems like in this new world of L4S, it might make sense to think of these kinds of speed tests as no longer really just a single speed test, but really there are sort of three different classes of workloads that we're going to have for a while. Like one is classic traffic that doesn't have any ECN support. And then the second one would be RC3168 ECN support, which I think you would often get if you had an Apple client device and a Linux server, which is a very common combination, obviously. And then the third one would be L4S. And would it make sense to think of the speed test world as one where we all need to start thinking in terms of really at least 3 speed tests to really get a sense of the dominant experiences that real users might have?
Yeah, maybe, because we're certainly running working latency tests of the classic queue as well as the second queue, the ultra low latency queue, and then thirdly, capacity tests that are running in the classic queue. Yeah.
Sorry, we have to continue. David?
Hi, Jason. David Black. Really good to see the AQM algorithms doing exactly what they're supposed to do in practice at scale. This is wonderful. I also want to strongly support your emphasis on measuring additional things. That which you cannot measure, you cannot optimize, has sort of the corollary, that which you can measure will get optimized. And therefore, measuring things that matter to your users just makes entirely too much sense.
Yep, agree. And, as a digression, about measuring things, the funniest was, as we were going through this initial discovery and we saw retransmits drop, one of the folks who didn't really understand the space said, hey, what do we have to do to increase the retransmits back into normal range? I said, no.
Sorry, we have to cut the line a bit short. Sorry, Jana.
Thank you.
So next speaker, is it Michael already? No? Yes, it is.
Can I use my speaker slot to ask a question? No, I'm just kidding. Well, I'll take it offline then. Okay, pacing. I'll take this and get started. Quick update of our draft. The point of the draft is to document what's out there. We give an overview of pros and cons and issues and how you would do it and what are the consequences of pacing. And we give an overview of how people implement it already, such that if you want to implement pacing, you can say, hey, this is exactly probably the right way for me to do it. I have actually had a hallway conversation with somebody saying that this draft was already helpful in terms of understanding how Quiche implements pacing. So that's happy news. An overview of the history of the document is, we started off with Linux TCP and Quick BBR, then added Vidi and Michael Tüxen as co-authors who added text on Apple OS and FreeBSD, both pretty short and pretty high level, but they both promised to make an update by the next version of this part. Then the O2 draft that incorporated some of the list feedback that we got, for instance, from Ingemar and from Eduard Vasilenko. Things about mini bursts. Eduard had that text that he suggested to say that it's important to stress how a very tiny gap on the sender side can become a really big gap or like a burst delay, can become really large as you go further down the line and then you get closer to the receiver and the bottleneck that has a lower capacity. In version 3, we added some more text on motivations for pacing. It's not like none of this text was there. There was some motivation, but there was a bit of a restructuring here. And some things were added. For instance, the fact that egg compression, egg thinning, and so on would not necessarily have any effect on the downstream, well, on the data traffic that you're sending if you're pacing. So you can compensate for these effects. You can operate with shorter queues that will create a better incentive. And when applications do use pacing as a vehicle to limit the rate, well, even below the bottleneck rate, then you will be reducing latency just directly, irrespective of the queue size. You get better RTT measurements. there can be benefits at the receiver of having a more steady workload. It can be better for some applications. We're not qualifying this as it's only good. It's definitely only going to help in these kinds of ways, but these are potential benefits. And some very special cases as well, even tip-top. Then there is also some extended text on mini bursts and some text specifically about, well, there was mention of TSO, but now there is also text on GSO, LRO, and GRO, all these offloading functionalities. And a little bit of text on application control, where we have things like SAMI coming from Netflix and Scream, which both let the application control the pacing rate such that it is a function of the actual video bit rate and a little bit higher, so that you don't risk being too late with your packets. But there is really no point in sending everything out as quickly as the congestion control allows when you actually have a bit rate of a video that is way below. So in the case of Scream, it's 50% above the bit rate of the video. There are a few open issues on GitHub, not too many actually, just asking for more detail on Apple OS and FreeBSD and some of the more general consequences of pacing. There's one particular paper that is quite well known on pacing that has discussed some effects and that I promised to look at, and I will, but I still haven't in detail. I mean, I did long ago, but there are things like synchronization effects and so on discussed, which may be okay and correct, or maybe not irrelevant and not relevant anymore, maybe overtaken by, well, updates, since this was an old paper. Previously, we had quite significant interest in getting this adopted. So I will repeat the question that I've asked earlier on, could we please adopt this? And that's it, I think.
Thank you for bringing this draft back, Michael. Does anybody have any questions before we go into the adoption discussion? Okay, not seeing any hands. I wanted to start by asking who has read the draft, and I'm starting a show of hands. So if you are not logged into Meetecho, here's your nudge.
Opinion is interesting.
No opinion on whether you've read it, I know. Okay. Already have quite a good number of folks. That is great. So that indicates there is significant interest still. Okay, but now what does the group think about ICCRG adopting this document and committing to working on it, seeing it through to publication? What did we already get? Oh, okay. So I see one no vote. Nope. Okay.
I mean, it's fair
Not a
enough.
no.
Saying I haven't read it.
Okay, well, that is overwhelming support already. We will run a formal adoption call on the list just to make sure any kind of considerations are brought up, or people at least get a chance to. But it looks pretty good.
Yep.
Any more thoughts from Michael? Anybody else in the room?
No, thanks.
Thank you for this incredibly useful draft.
Homework for you on the mailing list now. So, Zilly. So you can go until 5 after.
All right, so hello everyone, this is Zilly from the Hong Kong UST. Also a paper about pacing, following what Michael was trying to propose. And this is paper that we just got accepted to SICOM this year. So when I was seeing the draft in the ICCRG on pacing, I immediately signed up for our paper to try to discuss more on the effect of pacing here, also in the video streaming. So the title here you can see here is the burstiness control for the RTC or for the real-time video streaming scenario. So in general, it's the pacing and how that affects the stalls, the performance, the user experience in the video stream. Right, so very brief introduction, right? Everyone now is using the video streaming and in the internet for video conferencing, cloud gaming, and blah, blah, blah. And this is how the video streaming is being sent. I guess in the later panel, we will have more information from the panelists on that. So just skip that. Here, this work, we are trying to talk about the latency in the buffer between the application layer and the transport layer. So basically, if it's in TCP, this is going to be the socket buffer. If here is, let's say, in WebRTC or in any video streaming related applications, it's going to be something called pacing buffer. So the basic idea here is that, okay, video frames, they encode the data into a lot of frames and then later split into a lot of data chunks or data packets. But before the packets can be sent out to the network, they will first be put into a buffer and waiting for the sending opportunities determined by the congestion control or the pacing algorithms, or basically in the transport layer. So what's wrong with it? Oh, sorry. Oh my God, this is overlapping a little bit. So what's wrong with it? So you can see from this plot on the left-hand side, when the video frames are going to generate the frames one by one and feed the frames into the buffer. On the right-hand side, the network, or basically the congestion control, will try to send the packets one by one out from the buffer, right? So now if, let's say, we focus on the queue in the middle, which I denote as pacer here, the incoming or the ingress side is the video frames send the frame one by one into the buffer. And egress or outgoing side is the congestion control, or there's kind of some sending opportunity which will take the packets out one by one. So here is actually a mismatch. You can see here's a queue, and the incoming data and outgoing data comes from the encoder and network respectively. But what if they do not match? Surely they will match, right? Because recall like how we are going to set the target bit rate for the encoder. It is going to be the bit rate from the congestion control from network capacity. So they will match from a stationary or from the average perspective. That is for sure. But if we zoom in to a very short time scale, actually there will be two mismatches. One is the mismatch on the temporal domain, right? Frames are generated one by one in the granularity of frame. But one frame can contain like 100 packets. So let's do a very brief calculation here. If a video stream is 30 Mbps and the frame rate is 30 FPS, that will give you answer that one video frame will contain 100 packets. Looks like the average is still the same, but to network, if you immediately send this 100 packets out, it's going to be a huge burst, right? You cannot, for network, it's going to send one packet every probably 1 millisecond. It is not going to send out 100 packets every 100 milliseconds. That is not how network should send. So this is on the temporal domain, and the other domain is on the content. So this is due to the mechanism of codec itself. Codec has a mechanism called the VBR, the variable bit rate. So sometimes some frame will be larger, some frame will be smaller. The average size is exactly the target bit rate, but for the larger frames, they can be multiple times of the average frame. Here, just want to be clear, I'm not talking about the key frames or the iframes. They are all the P frames all the time. This is just because the contents are changing, right? Let's say you are watching a soccer game. If it's just some like randomly in the mid-court back and forth, there are not that many motion in the stream, then that's fine. But if the scenes or if the motion change a lot, then the frame size will also go up. So this is a mechanism that we pass over different codecs, including the 264, 265, and VP9, AB1, and so on. So we can see that even if for all of them are P frames, there will be 1% of P frames where the frame size will be 6x of the average frame size. Right? If you put this together, then that would be very huge effects. One frame is already 100 packets. If there happens to be a frame which is 5x or 6x of the average size, then that frame will be 500, 600 packets, which will be a huge burst to the network. Okay, so how to solve this? WebRTC has a very simple answer. Just do pacing. You paste all the things out. But this will cause a huge delay here. And we have two tests. One test is from WebRTC, which is from our measurements over a lot of traces, which you can refer to paper later. The pacing latency, which is the latency buffer, will be the dominating latency if the end-to-end latency is very high. So how to understand the plot on the right side, on the left side? If the end-to-end latency is above, let's say, 300 milliseconds, then almost 80% of latency here actually comes from the pacing buffer's latency. Because here, the assumption here is the congestion control like GCC, Scream, NADA, they have already done a great effort. So in the majority of cases, because they are already underestimating the network, so they are fine. And we later repeat the same test with the Binance, so the Binance Cloud Gaming. We find that it's the same in their online production environment. In the Binance, they also have the similar effect where the pacing but delay will dominate the end-to-end delay as long as the latency goes up. So the solution is very simple here. I will just briefly talk about the high-level ideas here. So we can think, because the issue comes from this queue, so how to make the queue be shorter as soon as possible? Surely two sources. One is you control the outgoing. The other is you control the incoming. So for the outgoing, we want to minimize the effect of pacing, which means we want to burst send out as much as possible. Why as much as possible? Because if you really send a huge burst out, then there will be a huge network loss, right? The routers will suffer from packet losses. We do not want to have loss. So we want to send out the burst as much as possible, as long as it does not incur a significant loss in the network. And the assumption here is that a lot of congestion control algorithms in the RTC, so in the video streaming or low latency domain, they are actually underestimating the bandwidth. This is because they want to have a low latency, so they have to sacrifice on the bandwidth. So if they are underestimating the bandwidth, then that's perfect. That's our opportunity to transiently, in a short period of time, send more packets out. For the in-queue side, remember the in-queue side, it is caused by the codec, so it is caused by the VBR, the large frames, small frames. We just want to mitigate those oversized frames. So for the in-queue side, we want to have less large frames. And for the DQ side, we want to control the patterns of pacing out. What did we do on the DQ side? So how to make the pacing be adaptive? Here we use a token bucket for pacing. Congestion control will control the sending rate or the token rate of the token bucket. What we will control here is we will control the token size of the token bucket. Because of the size of token, the bucket size, because of the size of the bucket will affect how large burst it will send out to the network, right? The larger the bucket is, then you will send more packets at once or in one time to the network. This will affect whether the network can absorb this burst or not. So we actually design another algorithm on top of the congestion control, which controls the bucket size. This is independent from congestion control because congestion control controls the average sending rate. It controls how fast the tokens are being filled into bucket. Here we control how large the bucket size will be. If let's say the bucket size is 60 packets, then if there's a frame with 100 packets arriving at here, the first 60 packets will be immediately burst out, and the remaining 40 will have to be paced following the token rate. And this size is determined by the loss. And for the in-queue side, let me try to be quick. The in-queue side is also very simple. Here, the observation is that the reason why we have large frame is because of content. We do have one skill, or we do have one mechanism which can reduce the frame size without affecting the video quality. Other thing here we want to ensure is we do not want to affect the video quality. Then how to do that? We can change the compression complexity. So the more complex the encoding preset is, the frame will be smaller under the same quality, but the encoding time will be longer, right? So for any codecs, like any conventional codecs, like in the plot on the right, they will have a different set of complexities, like very fast, ultra fast, very slow, and like so on. If you choose the more complicated encoding preset, the frame size will be smaller, but the encoding time will be longer. The opportunity here is if the cost on the encoding time is smaller than the benefit on the pacing delay, then it is beneficial for end-to-end delay, which means we will use a more complex encoding preset to save the buffering time in the token bucket, in the pacing buffer, with the cost of the encoding time. All right, I just skip the details here. So here are some, I just go to directly the final results. Here are some evaluation results in a lot of traces driven and also the real world scenarios in our campus in the Hong Kong UST. So we test our work, which is called ACE, with the Google Meet and also Salsify, which is a paper in the NSDI in the past. And we can now see that the latency and the quality of the ACE are actually almost the best against other baselines. So we also later put this in production in ByteDance, and this is the ByteDance result. And the start rate and the video quality is also much better than no matter you pace out or you burst out. And I guess that's it. And any questions? If you want to read more details, we have already posted our papers online, and we also make a talk in SICOM this year in Portugal.
No questions in the room. Yes, we have in the online queue. Neil?
Yeah, Neil Cardwell, Google. So it sounds like you're saying that the decision about the token bucket size is driven by figuring out a token bucket size that will avoid packet loss. Is that right?
Yes, I didn't go into details, but the high level idea is we want to minimize the influence on the loss. So as long as there's a loss, we will reduce the token, the bucket size. If there's no loss, we will try to estimate how large the buffering network can absorb.
I see. It seems like we care not just about packet loss, but also about queuing delay in the middle of the network. Do you think it might be worth sort of combining this with sort of TSO auto-sizing approaches, for example, the way they do it in Linux, where you compute the maximum burst size, but something like pacing rate times 1 millisecond or pacing rate times the maximum queuing delay you want to have?
Yeah, that's a very good question. So our thought on that was, you can see no matter you pace that out or you do not pace that out, the delay will always happen. Just the question is whether delay will be in a queuing delay network or it will be in a queuing delay in a pacing buffer. So we think they are equivalent. So
well, they're equivalent as far as your stream is concerned, but they're not equivalent in terms of the health of the general network and the delay experienced by other flows and other users in the internet, right?
Oh, that is true. The interaction will be different. So
yeah,
that's a very good point. Yeah, we will take that into consideration. Not for now, but I guess that's very worthwhile.
Now we have the questions in the room here.
Okay, this is Tong Yudai from Disney. I would like to know, I have two questions from my side. The first one is about you mentioned that there is no any quality degradation. I would like to know, do you have any specific quantified quality measures?
Oh yeah, we test PSN or SMV and other things, in the paper.
Yes. So what about the general like quality loss? If you would like to decrease the iframe, I expect there will be some.
No, we do not decrease the iframe.
Or general frame size.
Right. So here, the point here is, the first assumption is all the frames here are P frame. We don't care about iframe. Iframe we keep them as this as usual as original.
Oh, I see.
For all the P frames, the frame size will still fluctuate.
Okay.
Because the contents are different.
Thank you.
Right. And for those oversized P frames, we will try to reduce the frame size.
Okay.
Using a more complicated preset. If you are familiar with codec, we use different presets. So the quality here is the same. It just takes longer time to encode.
Got it. I will see the paper. And another question is about will you have any plan to open source?
Oh, yes, yes, yes. We will open source before the conference, so like in 2 months.
Thank you.
Janai Iyengar, thank you for the presentation. That was definitely very interesting. I want to piggyback on what Neil said earlier and carry it forward just a little bit. So if I imagine this as, have you done evaluations of multiple senders following the scheme, but sharing a queue at the same time?
Yes, so that's a very good point. We do acknowledge that this will have some interaction with congestion control when they are competing with each other. We did experiment, but you see that the experiment are always not that complete. So in our setting, it is fine.
No, to be clear, what I mean is multiple senders using
Yes.
your scheme.
Yes, yes, yes.
Because a lot of the problem here, so in general, the problem of bursts is not a local one, it's a network one, right? Like you're not buffering stuff, you're asking the network to buffer it for you. So you're externalizing the problem. And when you externalize the problem, what you have to look at is what you're doing to others who share that resource.
Right.
So that is like one of the evaluations I hope is there, or if it isn't there, I definitely recommend that you look into more closely, because the biggest problem here is going to be what it does to other flows in the network, not just to what it does to your flow.
Exactly. So for two other flows, we did experiment both with all the mechanisms using the same as us, and also with competing flows that does not use our mechanisms. So our results show it is fine because we use the setup in our campus and the Wi-Fi routers and hyper flows, different flows, cubic, BBR, different congestion control tests at the same time. That is fine. But I do acknowledge that this will have some synchronization issues. Right? Because you're sending bursts, which means if two bursts coincide at the same time, then one of them must be lost. So that's why later our token bucket is aware of that loss, and we'll try to adjust the bucket size based on that.
There's also a capture issue.
Where you have
two complementary flows that capture the queue. And I'm really curious to see how this will work with Jason's FQ pi in the network, because I think the two of them are going to like try to kill each other.
Would love to have a try.
Thank you.
Mozinati, I was unclear whether you were trying to integrate your bucket with the actual encoder's leaky bucket, because all encoders and in the decoder models also, they have this buffer model, leaky buffer model, VBV.
VBV buffer, exactly.
So are you integrating with the VBV of the encoders, or this is something outside of it and simulating it?
It is something outside, and it is independent from VB buffer. This buffer is after the frame is encoded and being sent to the network.
Right, but I mean,
we do have another work on VB buffer size. We can discuss that later. But this buffer is after the VB buffer.
Okay.
Which also exists in the.
But you're not trying to in any way communicate or harmonize those two, because they're doing the same kind of thing. They're both trying to make a temporal estimate of a long time frame and a short time frame, and trying to allocate bits to the long and short time frames.
We are doing that in another paper. Very good point.
Okay.
We can discuss later offline.
Yeah, thank you.
Yeah, the room is empty now, so we can move to our panel in the last hour. I guess we got a few extra minutes here, and you guys also asked to show something instead of just presenting slides. So we have to pass you the token. Sorry, just a second. Yeah, there you are.
Hello. Hello, good afternoon. My name is Ali. I'm with the Özyeğin University in Istanbul. I'm going to talk about live and real-time media today, something I've been working since 2001, including my graduate studies. So this is going to be, collection of bunch of observations and experience in the last several years. And most of them are my personal opinions, obviously. And I'll be more than happy to discuss anything in detail. So Okay, there's a couple of seconds of latency here. So what we are going to look at today is the following. So we are talking about live streaming, and this includes anything like things you watch on TV and on your devices, and then all the way down to real-time applications like WebRTC, video conferencing, drones, metaverse, and all that stuff. So we have, this is just a diagram from a paper that we just published a couple of months ago. There's a preprint version that you can access freely. It's a very long survey, but it includes pretty much everything about live streaming to date. So we have a spectrum of high latency applications, typical latency applications, low latency applications, and then ultra low latency is something I don't really like the term very much, but that's what it actually got stuck with the market, and then near real-time latency. So we have different types of applications. As you can see here, there are streaming media, which we have been doing for the last 2 decades or so, using Dash HLS, smooth streaming before that, and usually, typically using really long segments. And then typical latency applications today are most applications run at those latencies, using 6-second segments. And then what is really interesting for the last couple of years is the low latency applications, because this is where the streaming application will have a typical latency similar to cable IPTV satellite. So if you are watching a football game or a basketball game on your cable TV or IPTV, it's going to be anywhere between 5 to 10 seconds of latency. And if you want to get down to that kind of latency, we need to have some low latency streaming as well. And then going even further lower, we have gambling, betting, auctioning applications, which are becoming also very popular. And then at the ultra low latency, we have cloud gaming, conferencing, and all those other applications. So we are going to look into some of these shortly. So in 1969, just to set the stage, mankind has landed on the moon, and they actually did a live broadcast. I wasn't born at that time, but maybe some of you were. And people tell me that, this was really a great event. It was watched by 650 million people live on TV. And it's one of the greatest, live TV broadcasts. So the typical latency from the surface of the moon is more than 2 seconds because of the distance. But the broadcast latency was about 3 seconds. So they did a pretty good job in terms of achieving latency. 50 years later, there was a Super Bowl game in Atlanta, Georgia, where I went to school, and Super Bowl 53. And even if you were just a few miles away from the stadium, the latency would be around 45 seconds. Obviously, this didn't really improve very much, right? In 50 years, yes, we have much better quality digital video and everything, but the latency-wise, it really sucked. These are statistics from Super Bowl this year, 2025, and you see different platforms over there: NFL Plus application, official application, and then Fubo, Hulu, YouTube TV, Sling, DirecTV, and Tubi. This was broadcast on Fox in the US, and their application was Tubi. And the over-the-air broadcast, so if you just, Super Bowl is supposed to be on public television. If it is, if you are receiving just over-the-air signals, so nothing really fancy, the latency was about 16 to 21 seconds. Obviously, this has some profanity delays, due to some Janet Jackson issue in the past, sort of. And Tubi application was about 26 seconds of latency compared to the action on the field. So compared to the over-the-air, Tubi was doing a pretty good job. But if you look at DirecTV, YouTube, Hulu, they kind of really sucked, again, in terms of latency. So was that really the case? I mean, okay, this is going to be a bit slow, but you will get the idea. So we have been working on low latency since 2016. Personally, myself, and including many people in MPEG, Dash Industry Forum, and so on, we made it work. We specified the protocol itself, how it should work, and then everything. And then we gave it to the streaming guys, and that's really what they did. They really screwed it up. Until, I mean, today, still, if Super Bowl is not really being broadcast at low latency, there must be something really wrong. So Just to set the stage, we have broadcast on one hand, all of us are familiar with this, obviously. It is one-to-many distribution. Satellite cable, IPTV, doesn't really matter. It is fixed capacity usage, right? You might have 1,000 channels, you need this much bandwidth. You have 2,000 channels, you have this much bandwidth. It is fixed schedule, fixed devices, set-top boxes usually, or digital receivers on your TVs and so on. It is single and high-quality version of the content. So there could be the same channel in HD or SD at the same time, but it is still the same HD or 4K or SD for everybody. On the other hand, streaming is one-to-one distribution. You get what you want to watch whenever you want to watch it and anytime you want to watch it, right? So the capacity usage is variable, and obviously it comes with a lot of difficulties because of variable usage of the capacity. And on top of that, we have multiple qualities of the same content, so that we can actually stream it in in an adaptive manner with respect to network conditions. So the question is how we are going to exit the quality of broadcast. Now, HTTP adaptive, and the technical term is actually multi-bit rate streaming. People call it, and including myself, we call it ABR, but it is a misnomer. It's not really the bit rate is changing. There are multiple bit rates encoded at the same time, and then you just pick whatever you would like to watch. So we have a server, and then we have a client. Just a simplification, this is supposed to be CDN. So it's a request response based paradigm because it's HTTP. And then on the server side, we have all these different flavors, different resolutions of the same content, right? The client is going to use the HTTP stack. It's going to look at the playlist or the manifest if you are using HLS versus Dash respectively. And then you are going to continually look at different things like how much data I have in my playback buffer, right? What is my available bandwidth? And what is my CPU usage? I mean, do I really have enough window size to decode this and display this content properly and so on, right? And then the client is going to decide what to request next. This is what we call as rate adaptation or adaptation logic. And then you report, you measure, and then you report your success rate criteria and so on. All these clients are really smart. Servers are kind of dumb because you just ask what to request, for them to send back to you. But then the clients are quite selfish in the sense that they always try to maximize their own utility in terms of quality and other things. So what matters to human eye is, this is a very important problem, QoE modeling. Overall media quality is very important, right? Whether the content is high resolution, high frame rate, is it HDR and so on? Do I really have multi-channel audio as opposed to mono or just stereo? No lip sync issues and things like that. And then the stability of the quality is also very important. I really don't want to keep changing the resolution all the time. I don't want to really have stereo multi-channel audio switching all the time because it's going to be mostly audible. And then robust playback, we really want to have really short stalls or no stalls at all, like freezes. And then even if they are going to happen, hopefully they are not going to be that frequent. And we would like to have a fast startup and fast seeking. And then especially for live stuff, which is the focus for today's talk, is proximity to the live edge. I mean, maybe you are living in the middle of nowhere, so you really don't care how far you are behind the live action in the field. But if you are living in a public society, if you are chatting with social media and so on, latency is going to matter to you. So when we talk about latency, this is what we mean. All the way starting from the source, there's a football game in the field or so, and then that stuff is going to play on your screen, right? And then this is the entire workflow, and sometimes the streaming is just getting the signal instead of the contribution encoder, it's getting all the signals from just a satellite or another over-the-air service, or maybe it's just AI content, right? So this part is going to be the OTT latency, over-the-top latency, and this is going to be the end-to-end latency. And this is the latency that we are talking about mostly. And these are the factors that are going to affect these latency values. How much time you are spending on your encoding, packaging, ingest, obviously network propagation, server IO delays, license key fetching, because sports content is most of the time is encrypted. And then you are going to decrypt the content, and then your player, how is that going to behave in terms of buffering and rate adaptation logic and so on. So coming back to our time scale here, we have Dash and HLS that have been running for a long time in the field. Between 2 and 10 seconds is usually the norm, and the shorter the segments, the lower the latency you usually get. But you cannot really make extremely short segments because of the encoding inefficiencies. And then for that, we have low latency Dash and low latency HLS extensions. Low latency Dash came out around 2017, so like 8 years ago. And then low latency HLS came out in 2019, 2020. So they have been around for some time, right? So if you want to go further down in the latency, obviously we got to do something. And this was a conference that I organized during COVID times in Istanbul, ACM Multimedia Systems. And Twitch, which was one of the front runners in this low latency live broadcast business, they organized a grand challenge, like a competition. They said, we want to have some rate adaptation algorithms designed specifically for 1 second latency. So a broadcaster, let's say from Brazil, they want to broadcast their gaming to viewers in Europe, North America, anywhere in the world, and they want to have a single second latency. And there's a blog post, there is a report from Twitch findings, you can all look at these. And out of this grand challenge, actually, some really cool algorithms came out. We couldn't win the competition. My students actually entered the, we wanted to win it, but we were the second. So this is the algorithm we came up with at that time, 2020 and 2021 timeframe. So this is going to be a bit complicated, so I'm not going to go into the details. Here is the paper again with the link, and then here is the source code. But we have the throughput measurement module, as you can imagine. I'm going to talk about that shortly. And then we have some learning model-based ABR algorithm, SOM model. We have adaptive playback speed control, which I'm going to talk about as well. And then everything is included in one package. And then this guy is trying to achieve the latency you want to achieve at the best quality possible. So low latency, and again, this is primarily for sports content. Nobody's really interested in low latency finance or other types of news, I guess, but low latency sports is the big market for this. So you got to implement some sort of adaptive playback. And when I say adaptive playback, I mean that changing the playback speed just to be able to keep up with what they, how fast or how slow the data is arriving at your client buffer. So sometimes maybe you are running really low on your buffer, and the data is not arriving as fast as you would like to, so you are going to slow down the playback a bit. And then eventually you need to catch up with the latency, so you got to accelerate your playback, right? So adaptive playback has been around for some time, and we also did some content awareness into this. And this is really because you don't want to change the playback speed arbitrarily during the playback. If Messi is going to shoot a penalty, you don't want to really mess with that, right? I mean, the guy's name is Messi, but you don't want to really mess with it. Here is a demo, a very quick demo. Again, the details are in the paper. So we have this live encoder, FFmpeg, and we have a CV library, OpenCV, and then we are integrated into this FFmpeg. So while this is a pool game, it was easier for us to play with the pool game. I'm going to play the video to you. When there is something important or something interesting happening on the screen, which is in a pool game, it is very easy because you understand based on the motions of the balls, right? You don't want to change the playback speed. But when there is not really something interesting, I mean, when the balls are stopped, the guy is just thinking and so on, you can change the playback speed very easily, right? And that's just an illustration of how content awareness can be built into this. Now, coming back to this throughput measurement is extremely important, and I see a lot of people doing stuff with this. In these multi-bitrate streaming systems, client side is the responsible side for selecting the bitrate that will request from the server side. So it's gonna this bandwidth measurement is gonna happen on the client side, and then there will be some sort of smoothing, and then maybe eventually some prediction. So we collect the measurements. Obviously, we make a request, we get a response, and then we try to understand what's happening. And then, these are going to be raw samples, and we are going to apply one way of smoothing. It could be weighted, it could be windowed, whatever you like. There are different ways of doing this. And then, by using newer parts of the dash as well as CMCD, CMST standards, we can collect some sender-side signals, and we can input that information into our smoothing operation. And then we are going to come up with a bandwidth value, and then you can use this directly as your bandwidth measurement, or you can feed into this a prediction engine. And that will be machine learning based or some AI based tool. And the better prediction you make, obviously, the better rate adaptation you are going to achieve. Now, most of the time we deal with the measurements in a passive way, and then it has a lot of advantages. Obviously, there's no extra traffic. You are just looking at the traffic that you receive and so on. And, it just works. But sometimes, especially in real-time applications or in really, really low latency applications, passive measurements may not really work very well. So you might need some active measurements. And then they have some advantages and then disadvantages too.
A quick clarification question. If that's
Yeah,
okay.
please.
What are the sender side signals you're using here?
Sender side signal could be just this is how much my congestion window size right at the moment. This is how much I think I can send it to you. It could be any type of information the sender is willing to share with us.
Well, are you doing this, or is this just proposed?
No, we are doing this.
Okay, so the signals you are sending are window size.
So in our implementation, the server has a measured throughput value to the client, and then it tells that client, this is how much I think I can send it to you.
Got it. So it's the sender's view of the world that it's.
And then the sender tells you this is 10, and then you measure 9. Well, maybe you're going to go with 9.5. It's up to you, right?
I see.
So you get multiple inputs.
Thank you.
Yeah, but there are different ways of doing that too. Now, one thing that really comes up, from time to time is, should we really do this on the client side or the sender side? Obviously, server guys want to do on the sender side, client guys want to do on the client side, but I think there should be some sort of a collaboration here, like, jointly working. And I am one of the guys who is in the camp of client side measurements, but we should use whatever information the sender or the server is giving us in terms of bandwidth measurement. Now, all right. So, yes.
Yeah, can you go back one slide? Yeah.
There's really a lot of latency between slides.
Yeah, there we go. Mozinati, I'm glad you bring this up because I think this is the classic problem in all of congestion management, and we kind of ignore the problem or don't even realize the problem. Maybe it's not ICCRG as much as maybe like CCWG or even the individual protocol senders. What you're describing here is things that are happening in one specific application, right, for one specific kind of sender. But really, there's a general problem of the receivers don't have established ways to have these sender signals given to them, and vice versa. So all the APIs and things that are exposed are about send rate. I'm controlling my send rate. I'm a congestion controller, and I get generic ACK feedback from something, and I control my send rate. But at a client, you don't really care about your send rate. You want to know what is the target receive rate, because I need to know what to ask for. I need to know what resource to get. And all the congestion controls are about, I already think I have this resource, and I'm just pushing it, and I need to know how fast I can push it.
Yeah.
But they don't solve the client side receiver. What do I need to pull?
Yeah.
And we're doing it in every specific application in a different way. And it really probably should belong in some kind of generic signaling for all applications, because it's the most critical piece that's missing in linking the senders and receivers to match the rates.
But, I mentioned two standards, CMCD and CMSD, and Will is one of the main guys behind that. And, we developed those specs just because the transport layer itself doesn't really give us what we need, right? We need to improvise at the application layer to get whatever information we think.
But are they dash like profile, specific specs? They're not, or
Not
they're
really. I mean,
general media.
those. I mean, it could be easily used for HLS or Dash. I mean, it's not really specific. Then it's streaming format, and mock can also use something similar. I'm just saying that it is independent from the transport layer. It's the application layer giving you that information. If there are some APIs to give this information or get this information from the transport layer, sure, why not?
I don't know where we should standardize something like that in IETF, but I think maybe not ICCRG, but I think that's a big missing piece for all the applications.
Yeah, good comment. All right. So one thing I just realized that I forgot. Most of the time we use this smoothed value for our ABR logic, like a rate adaptation logic. But then if you want to do prediction, which is really like predicting the bandwidth, what it's going to be in the next several seconds, not just immediately, that's going to be helpful for your rate adaptation. So let's look at a couple of models here. I have 5 more slides. Yeah. So different networks require different prediction models and things like that. So, based on some public data, we trained a lot of different models. And again, I'm not going to go into all these details. They give different performances in different environments. But the idea is that whatever your environment is, you got to pick the right prediction model and then predict the bandwidth for the next whatever steps, like next 2 or 3 or 4 steps, and then perform the rate adaptation accordingly. Now, this is something we implemented in open source. Again, the code is available, and in Dash.js, it could be easily incorporated to other players, bandwidth measurement, bandwidth prediction. By just changing that module in the public, or existing implementation, we can improve the performance of the ABR algorithms. Like Pensive and MPC that came out some years ago, the accuracy of the bandwidth prediction can be improved significantly. And that's my DMAX talk from a couple of years ago. It's on YouTube. Again, now coming back to the last piece of my latency diagram. Obviously, we have this Dash HLS and then low latency Dash HLS, right? And then what are we going to do with all these applications? Real-time video, right? WebRTC applications, Zoom, WebEx, and all that stuff. So, WebRTC obviously exists for a long time. And then, some people tried to use WebRTC for large-scale streaming or, events. And, for some people it worked, some people it didn't really work because of scale issues. And then for the last couple of years, we have been working on this media work quick in the IETF, right? 2.5 years. So MOC was envisioned to actually fill that gap, little gap between low latency and ultra low latency barrier. But the more we played with that, we realized that it could actually do pretty much anything we could do with all the existing protocols. I can today implement media work quick, and we have our own implementation. I can do just Dash HLS, what Dash HLS can do, or I can also do what WebRTC can do. So it's a single protocol that will pretty much potentially replace everything. Again, coming back to this multi-bit rate streaming, it is not a receiver-specific encoding. So it is multiple bit rates already generated by transcoder, and the receivers are going to ask for different versions. This is what I need, and please send it to me. And then again, this is what I need, please send it to me. It could be the blue version, the red version, whatever combination, right? But in real time, we have other things to work with. It's going to be a single bitrate encoding like WebEx or Zoom or FaceTime, right? We are going to say this is how much bandwidth I have, and the sender is going to adjust the rate control in real time to be able to send at the best quality to you, right? So this really is receiver specific encoding. Now, why we are doing this all in media work quick? Quick has all this flexible loss recovery, and it gives us the capability to do latency aware operations. This is especially useful when the encoder's rate control is not fast enough. So let's say this is these are my frames, a bunch of frames. The black frames are iframes or keyframes. And now if something happens to packet number 4 or frame number, in this case, it's going to be lost. And if it is a TCP traffic, like a regular Dash HLS streaming, it's going, TCP is going to try to recover, forever, right? It's going to be head of line blocking over there. But the quick can do a lot of different things. Now, it can do what TCP can do. It can continue with the next cop and skip the current cop. It can continue with the next cop and then come back to the current cop. Or it can actually use the missing information by using FEC. We all implemented this, and then they all have different advantages and disadvantages. Last information here for real-time media rate control. We have developed this BOB bandwidth prediction for real-time communications. So as opposed to just Google's congestion control algorithm, GCC heuristics, we have a deep reinforcement learning module as well here. And then it's a hybrid in the sense that it can run both heuristic as well as the error controller. So you can it can switch between those two and then decide what the best rate should be. So there are some advantages and disadvantages, and Simone is just pushing me to finish my slides. Just to show you some results here. Again, these are from the paper. Different. Again, these are Grand Challenge competitors, winners, the first one and the second one, and then actual bandwidth. As you can see, the idea is to be able to track it as close as possible. Now, I would like you to see our implementation of MediaWork. This is actually based on the Mocha REST library, not our own library, but we are going to soon port that as well. This is MediaWork with client-side ABR and then low latency dash. You can run them in parallel on the same screen, and then you are going to be able to play with different network profiles and things like that. And you are going to see what kind of latency or quality you are going to get. It is at moq.streaming.university. And this is the last slide, what we have been working on, my students and myself. A lot of things that I mentioned in this presentation. Congestion response policies, that's one of the primary things in the MediaWork. The current draft obviously just mentions this, but doesn't really talk about the details. Selective drop policies, what's going to happen in the network, in the relays. And we want to improve the, when there's congestion, but we still want to keep the quality at maximum level. And subscriber side or client side track bitrate selection logic. I mean the ABR. Publisher side rate adaptation, encoder controller, prioritization schemes and scheduling strategies. And this is all going to, as we implement things, this is going to be incorporated into our own implementation, Mocktail, which is available at mocktail.dev. And that includes my presentation.
Thanks, Ali. Jana.
I'm happy to have some questions.
Jana Iyengar, are we really like 35 minutes? Okay. The question is more of a response to what Mo was saying, which is why I waited until the end. And it was about the sender and receiver side working together.
Yeah. There's something wrong with microphones.
Yeah, I think that the streaming in particular is a very particular type of application that enables this. Typically, your applications don't have this degree of freedom because they're all trying to get traffic as quickly as possible. That's normally the case. There are very few applications that don't care about that. But I'm glad to see that you're pulling in the receiver side thing. I think that's really crucial. I'm pulling up, the Tiva is going to talk about this from the Netflix side next as well. But I think that's a really valuable thing to do.
Yeah.
I thought you wanted more time, but you're done or you're
I'm
fixing
done.
the
I was
mic?
just fixing the mic.
Yep, just Yeah, thanks, Ali. So I think we don't have anybody in the online queue. TY.
Did I stop sharing?
Cool to bring this video people here. You always have something to show. Yeah. Yeah. I guess you got it now. Oh gosh, I need to quit and reopen, of course. Maybe got 1 minute to warm up. Did Did you get
Yeah,
from Reese?
yes, just Chrome asked me to quit.
Okay. No worries. So we still have half an hour.
Okay.
So feel free to use the time.
I just requested again.
Yeah.
Yes. All right. Awesome.
Yeah, great.
All right. Thank you, everyone.
You want to, I think it works.
I need to connect to this one. Right?
Okay.
There, right?
Oh,
Do you have the connector?
no.
No. Okay.
Did everybody get the connector from the?
Okay. There we are.
You should use your keyboard.
Okay. Yeah.
Missing the USB using.
Right. All right. Thank you, everyone, for being here. My name is TY. I lead the adaptive streaming algorithm effort at Netflix. Hold it. Easier. I'm here together with many folks from Netflix who is on the congestion control side. And thank you, Mo, for the question, because that really tees up this talk really well, because we are going to talk about the direction we are heading together between adaptive streaming algorithm and congestion control. And the direction we are working towards is really about combining these two parts. And the reason for that is over the years that what we observed is that adaptive streaming algorithm and congestion control kind of need to work together. And if we work together, that actually brings down the burstiness and also brings better QE. And so, and besides what's our observation, YouTube is actually trying a similar idea, and they are also seeing a similar benefit. And so if there's one thing I can have you take away from this talk, that would be combining these two logic into one. It's actually pretty good for everyone because less bursty traffic, I think I'm seeing to the choir here, everyone believes that will be good and it's actually pretty good for everyone. And if you are in a position to do that, you should try it out. And IETF or IRTF being a standard body, if we can figure out that API Mo was asking about to do so, then we as a community should try it out and do it together as well. All right. So in order for me to show you like why working together, these two logic, which conventionally, as Ali was showing, that they kind of work on top of each other. In order to show that the benefit of them working together, we kind of need to go back to how they are working together today. So for APR to work, of course, initially we just need to pick an initial bit rate. And then we use that bit rate to download a few video chunks through TCP. And what the APR will be doing is it will do the measurement on top of what the TCP throughput delivered to the APR there, and then use that information combining with the player state, such as buffer occupancy or device capability, etc. Then we will, the APR will pick a video bitrate based on that. And then it will take a look at the buffer occupancy to see whether there's a space to download this video, and if so, then the control loop just continues. As you can see from this control loop, the decision from adaptive streaming and congestion control kind of intertwined with each other, right? And in the worst case scenario, they can actually interfere with each other. This is a work I presented here in IRTF eons ago. But what the problem here was that when the adaptive streaming algorithm being conservative, that actually fit into the congestion control information and then deliver a pretty low throughput. And that information got feedback into the APR control loop and choose an even lower bit rate, and an even lower bit rate will make TCP download even fewer bits, which make it less competitive with competing flow, and and you will just drive down the bitrate selection. So they can interfere with each other if they kind of work independently. But if they work with each other and share information with each other, we can actually achieve pretty nice things together. So what's wrong with this picture? And what can we do and make it better? And so the fundamental problem here is that congestion control is a generic logic, and it is trying to fully utilize the fair share to download the video. And so what it does is when the adaptive streaming algorithm asks you to download the video, you just don't try to download it as fast as possible. The problem is that video today is not, most of the time, is not throughput limited. So if we look at how the average US internet evolved over time, and I'm pretty sure the European internet is even better than the US. And so if you look at how the speed was evolved over the last decade or so, it was increased quite significantly from 5 to 200 megabit per second on average. But if you look at how the video bitrate grows, it is not as fast. And that was mostly thanks to how the encoding technology has evolved, even though the resolution, the top resolution over time was evolved into 4K. But the top bitrate is still pretty low compared to how the internet speed grows. And so, of course, depends on the content complexity. The top bitrate will be different. But kind of in the worst case scenario, it's only about 20 megabit per second. So if you compare the throughput and the top bitrate we need, from Netflix data, what we see is that the average playback session, their throughput is about 13 times more than the top bitrate they need to have. And so instead, so what's happening in this control loop is that when the congestion control is trying to download each video chunks as fast as possible, plus the fact that most of the video player has a limited of playback buffer, and we have a much higher throughput than the video needs. All that combined together, that means we have a pretty bursty video traffic. So what usually happens is that in the beginning, the video player will try to build up the playback buffer. And so as a result, TCP has a lot, or congestion control has a lot to download. And so we will fully utilize the bandwidth. At some point, the playback buffer will be full. And so we will have to make the network idle and wait until the playback buffer drained to the point that we have enough space to download the next segment. And then we fully utilize the network again, fill up the buffer again, and then wait and rinse and repeat. So what we end up with is this kind of notorious on-off, bursty video traffic that we see. But it doesn't need to be that way, right? So in an ideal scenario, maybe in the beginning, we still need to fully utilize the bandwidth. But after we have done so, then we can actually slow down and only download our video chunk as much as we need it, not as fast as possible. And if we do so, what we will see is the queuing delay is going to go down. The packet loss is going to go down. And if there are some other applications sharing the bandwidth with us, they are going to have a much smoother available bandwidth to share with. And to showcase the benefit, my colleague Scott, who is also here, he made the following video just to demonstrate how, when we pace our video traffic similar to what we're seeing in the ideal case, what's the benefit that would be to the neighboring the coexisting traffic. So in this scenario, we have a Netflix gaming session, share the bottleneck link with our Netflix video sessions, and we are going to do a screen capture on the video, on the gaming client. And all right. So what you are seeing on this screen, all right, here we go. All right. Uh-oh. Okay. Um, uh-oh. Well, the video is buffering. Okay, so what you are supposed to see, so on the upper side is the gaming session coexist with paced video session. On the bottom side is the gaming session coexist with unpaced video session. Oop, oop, oops. Okay, so well, what you are supposed to see is the paced session. The gaming session coexists with the paced session has a pretty smooth gaming session versus the lower portion, you will see some blocky effect. But I guess it's all blocky and stuttering all the same. Yeah, it's kind of weird because we can actually see here. So maybe I'll just highlight one part. So does it come? All right. You will see some blockiness. There we go. Never mind. You can see it. You're welcome to see to come to see at my screen afterwards, I guess. All right. But you get the idea. So what we observed and realized is that for video streaming application in particular, we don't really need to download as fast as possible. What we need to do is we need to download as fast as needed, which is different. And so that's what we so-called application-informed pacing. And the idea is really to flip the concept of adaptive streaming algorithm and congestion control around. So before, what it works is that adaptive streaming algorithm decide which bitrate we should pick from based on the throughput that TCP or congestion control can deliver to you. So here we are proposing that there needs to be another information loop. That is, the application there, the adaptive streaming algorithm, also need to tell the congestion control algorithm, like how much do I need? And they should work together using that information and combine this information together. So, so what we are trying to do with the application-informed pacing is that for the ABR to calculate what is the minimum throughput that is needed. And so a simple algorithm that we implemented in the SEMI paper, which we presented in SICON 2003, was that, hey, maybe we can calculate, we can provide that information based on the buffer occupancy. So in the beginning, when the buffer is low, then we can tell the TCP, hey, the top bit rate is actually a higher rate. So we set the rate in the beginning as a higher multiplier of the top bit rate. And as the buffer occupancy get higher, as we accumulate more buffer in the player, then we can use a much lower multiplier to the top bit rate. And if we put this into perspective compared to the average throughput that we observe, which is 13 times of the top bit rate, it is a very smaller margin according to compared to that. And so, and we tried it out in production, and we see a congestion-related metrics lowered all over. So the instantaneous throughput got lowered by 60%, the retransmission rate got lowered by 50%, and the round trip time lowered by about 20%. And all of that comes with QE improvements as well, and you can see the paper for detail. And so this observation is really pointing towards a promising direction that combining the logic between adaptive streaming algorithm and congestion control has a lot of benefit. So what's now? As I mentioned, that YouTube is also experimenting with a similar technique, and Ian is in the room, and you can ask him for more detail. And we are also in the process of rolling the application-informed pacing out. So there are some productization consideration you need to think about. So for us, we need to look into the CPU consumption. So pacing does consume more CPU, but in return, you also got lower transmission rate, which reduce CPU consumption. So these two things kind of work together. And another thing that we are looking into is the on the client side, when we do pacing, it does increase the time to receive. On mobile side, that means the radio needs to be open for longer. So we are working with Michael, who is also in the room here, on power consumption for mobile. And what we have observed so far is that doesn't really make much of the difference. So we are on track to fully productize the application-informed pacing soon. And YouTube and Netflix, we are also working together to quantify the benefit from both of us pacing our video traffic. So if you want to try it out, please let's chat. And this is my information. Thank you.
Do we have any questions? Yeah.
Hello. From your description, I guess your ABR is implemented in client side.
ABR is on the client side, yes.
Yeah. How about implemented in server side so that it can interactive with congestion control more effectively?
Well, as I mentioned, that ABR need to take player state into consideration. So ultimately, you still need to take the client information into consideration. So we still think on the client side is the best way, best position to do so, because you have the most direct observation, and you don't need to communicate that back.
If we have SAM-CD or SAM-SD, is it feasible to implement it on server side?
I think different service might have their own consideration. So for us,
got it.
yeah, it works the best on the client side.
Awesome. Another question is about a realistic problem. You are going to select to behavior more conservatively to be a nice neighbor, but in the public network, maybe your neighbors are not that nice. Even some companies select to behavior more aggressive. So how do you think about this problem?
I think this is a common problem, right? So TCP also, congestion control community also have that problem, right?
Yeah.
So not all congestion control algorithms behave the same way. So how does the congestion control community solve that? We kind of keep each other honest, right?
Yeah.
And so that also apply here. We as a community need to keep each other honest on how we share the bandwidth together.
Okay, thanks for your answer.
Alessandro Ghedini, Cloudflare. Thank you for the presentation. It was very interesting. You have a couple of questions about the implementation, maybe. The sort of, I guess, API between ABR and the congestion control algorithm, is that just setting, say, the maximum pacing rate for the congestion control, or like, do you need to pace a specific rates for this to work? And the other question, I guess, is how often do you see this like needing to be updated throughout like a connection or a session?
So we are communicating that at the segment level.
At the, sorry, what?
Video segment level.
Oh, I see. Okay.
Yeah. And so, and your earlier question is, how do we set the rate? So basically, we tell the congestion control, this is what we need. And then they translate that into the
So
level.
is that like a maximum rate limit that you set, or just like a specific rate?
Yeah, it's a maximum, because in some sense, if congestion control need to kick in and deliver a lower rate, they have to do that.
Right.
Yeah.
Thank you.
Hello, I'm Jian Haoyuan from TikTok Lab. I have a question, and I heard that YouTube has passed the client's information to the server to influence the CC algorithm. Actually, we are doing the same thing, but on the opposite way. We collect on the CC information from server and to influence the client side API decision. So I have a question. What's the interactive channel of YouTube?
Oh, maybe you should ask the YouTube folks.
Like CMSD, or what's the interactive channel?
So for Netflix,
Oh,
so
sorry.
yeah. So if you are asking about YouTube, you should ask YouTube
okay,
people. For Netflix, we do have a side channel communication between the server and client.
It's
And
working on a layer 4 or layer 7?
um, s-
The
um,
transport layer or application layer?
we have multiple ways for the server to and the client to communicate. Yeah, and so there are multiple
Okay,
ways for us
and
to do
how
so.
about the delay between the interactive signal?
So as I mentioned, the frequency that we are communicating this is per segment. So it's working right now. It's working at the HTTP level,
HTTP
and
level,
so
okay.
yeah, so it's more than a round trip.
Okay, thank you.
Hey, Will.
Will Law Akamai, hey TY, thank you. I'm a big fan of your pacing, as you know, and I think both Netflix and YouTube are in the lucky situation that you control the distribution chain, right? Control the server and the client. And there's a lot of media applications that don't. So I did want to point out, for those considering implementing this, that there are some standards that players that don't know the CDN and CDNs that don't know the player can leverage. On CMCD, there's a standard way to decorate what is the bit rate of the video. And a CDN can set a policy to say we're going to deliver at a maximum of X times this, and it can read it from the data that's coming from CMSD on the origin. And on the CMCD side, on the client, we standardize a metric called requested throughput, which also does exactly what your does. It says don't deliver it. I don't need it any faster than this. And I think if we got a lot more interop and standardization on both of those, then we could have working systems outside of the vertically integrated environments.
Yeah. Yeah, I think Akamai, if Akamai can, sounds like Akamai already provide these interface for any of the streaming services that would want to do so, and I would encourage people to take advantage of that.
We don't provide it yet, but I'd love to provide it so
okay.
people are interested.
So yeah,
yeah, no false advertising here. And say, I think Jinghua on the prior one raised a very interesting point that we're looking at all of this information exchange on a segment boundary, meaning every 2 seconds or 4 seconds you're getting an update. As media gets faster and faster and faster, and we go to say 400 or certainly sub-second communication, then we do need a faster way to transmit changes, because changes are happening at a rate that is greater than the 2-second temporal. And I just wondered if you had any insight into standardized schemes or algorithms, particularly at the application or the transport level, that can be used for that transfer of information.
Yeah, I think there are a lot of several very interesting research questions that we should look into, like what's the granularity of time interval that we need for what application. For video on demand, we especially after the buffer builds up, we don't need to react to the network changes that.
This would be
often.
for live video, like real time, us speaking to each other.
Right. Yeah. So, but even for that scenario, we still, for live, we still have like a second or two, at worst, right? Usually we still have a second or two buffer. It's not RTT level.
For your sports live, but for applications where it's real time, we want to talk to each other, we only have 300 milliseconds, say, as a threshold. And we can't wait for these segments.
That's
I don't want to
true.
take up my time.
Yeah, but I want to point out that this is also something like cloud gaming is doing, right? And they actually are already combining their rate adaptation algorithm and congestion control. And so I think there are a lot of examples that we can look into, like how people combine these two logic. And in cloud gaming scenario, they use they use our TCP to provide that feedback at the frame level. So
ABR and congestion control, like two blind people trying to communicate. I think we should help. Thank you.
right.
Mosinati, it's interesting that you're here showing the benefits of pacing, and two presentations prior, he was showing the benefits of not pacing, right? The penalty of pacing. So I think what this clearly shows is that the congestion controls that are designed are not taking the right application signals into account. And there needs to be standardized APIs for all applications, not just for video streaming or a real-time video application, but for all applications. There needs to be a finer grained API and control loop between the congestion controller and the sender and the receiver feedback loops, which are operating on much longer, control loops, but they shouldn't be. They usually care about things at the sender congestion controller's control loop time, because whenever it changes its estimate of what it thinks, that's when the receiver should react and do something differently. And I think we're missing that. And that's why you see conflicting proposals, in the same session, because we don't have that fine grained interface between the congestion control APIs and the applications. And it's not a single static number. It's a dynamic control loop that needs to be constantly evaluated between sender and receiver. And we're missing standardizing that.
And this is IETF, right? So if
Yes.
any interface can happen, it will happen here. So we as a community, we should keep talking.
And one final point on this specific proposal, a naive way would be just to pace based on your current, selected ABR rate. But you're most likely want to figure out, can I deliver my next level of the ladder? And so you may want to pace at the next level of the ladder to see if you can deliver at that rate. And that conflicts with things like BBRs, probe up and probe downs. Those probe ups and downs should be at the rate that the application wants, not a static 25% or 80% of the 125% or 80% of the bandwidth.
Yeah.
So it should be what the application needs. If the application wants 50% more bandwidth, maybe that's the more useful probe than an arbitrary probe.
And so that's why what we are proposing here is actually a combined logic, right? It's not if you continue to have two separate logic, they will interfere with each other, as you pointed out. Yeah, but there can still be some API, as Will was working on this CMCD, and those can work for certain applications. So you're right, depends on the application, the needs might be different. But for video specifically, I do think there is an opportunity for these two logic to work together and simplify a lot of things.
Let's hope.
Janai got a gentle correction. This is the IRTF, not the
Oh, sorry,
IETF.
IRTF.
No, it's all good. We don't. If you started to standardize in the IRTF, I think the chairs would have something to say about that. But I want to also disagree with Mo on that. I don't think that there's a standard here per se. The value of this presentation and the work to me is that it shows that ABR and congestion control can work together. Now, the shape in which that happens is going to depend on the particular needs of the particular application, as TY mentioned earlier. But I will also say that generalizing this beyond the immediate needs of the application that we're talking about here, which is streaming, potentially gaming, to other applications is very hard to do. This is like a very particular type of application that has the ability for a client to say, I no longer need this content from you if you can't deliver it to me within this certain amount of time, and so on. And that's a very particular type of application. So even if people were to think about this broader, I would stick to the applications, very specific applications that you're using, rather than try to generalize it beyond that. Thank you.
Yeah, agree. But I also want to point out video traffic is like 50, 60%.
Oh, I'm not saying that that's not most of the internet. It's perfectly fair to say that, for the internet, that this is useful. I'm not disagreeing with that at all.
So yeah, I think for the first time in the last years, we maybe finished on time. Jason, you want to make us
Sorry,
be delayed
Jason,
again?
just one last comment. I think that what happened for a lot of years is that the congestion control space at the transport layer was sort of ossified and hadn't changed in a long time. And so the video streamers had a real problem to solve, and they started sort of doing something, you know, obviously layer separation. So doing something at layer 7 to sort of adapt. Now you have a lot more innovation happening at the transport layer. And so the question is, you know, how do we arrive at a new, you know, equilibrium here? But it's exciting to see that both these layers are working at the same
Yeah.
time on the same problem.
Yeah, I think a bit of the intention with this talk and panel here was to illustrate a bit the problem today. I mean, we have had RMCAT many years ago, and people were talking about that back then. The working group died, and we have now other things that are not only video streaming, not only Netflix content. If there is interest that we sort like document, as I said, we have the opportunity to create a document in the group as well and put some people that are working on these problems to, it could be a benchmarking, it could be standard benchmarking, it could be just to illustrate where you have signals and interfaces, applications, and between application and transport protocols. This is the intention that we had here. And I'm glad that we have some discussion. We can continue on the mailing list. Don't let the thread die. So thanks again.
Very confused. I think I understand it.